Assalamu alaikum everyone. Okay, lecture 33 is gonna be a tutorial where we're gonna give you some hints about a couple of problems. The first problem we're gonna start with is the startup of a constant volume CSTR. So as you can see, we have a simple reaction. A goes to B and the feed consists of A only. Well, of course, the product will have both A and B. And we have a startup of a constant volume CSTR. Consider the first order liquid phase reaction that is carried out isothermally in a well-mixed constant volume reactor, initially filled with the solvent only. Assume the density of the reaction mixture remains constant during the course of the reaction. Therefore, we'll end up with epsilon equals epsilon naught. Additional information, so the value of K is given, the volume of the reactor is given, Ca naught is given, and epsilon naught is given as well. Type. For the startup period, perform mole balances on A and B in terms of Ca, Cb, and other constant. Of course, you're not gonna write mole balance in terms of X because X is wrong, right? Give you a wrong result because you have part of A accumulating and part of A is converting during the startup. So you cannot use X, which reflects only conversion. Okay. Right. So I'll leave you to do this. Part 2. Use the derived ordinary differential equations to plot the concentration of A and B as a function of time. Okay, so you have dCA by dt and you have dCB by dt as well. You're gonna solve these two equations to plot Ca and Cb as a function of time. Do both Ca and Cb achieve their steady state values at the same time? This is the question that you need to answer. Calculate the steady state values of Ca, Xa, and Cb. Okay, so at steady state, how would you calculate this? Well, you have many options. First of all, at steady state, dCA by dt equals to 0. So you can set it to 0 and then solve for Ca to get the steady state Ca. You can do the same for Cb. What about X? Well, if you know Ca at a steady state, you can calculate Xa from Ca and Ca naught. Okay, how else you can find the steady state value? Well, if you are not going to calculate it, if you want to find it through the plot, so we just keep t very large, give t very large value until the Ca reaches a steady state and Cb reaches a steady state, and you read it from the figure. You can do that if you were going to find it through the figure, but here it says calculate, so you need to use the equations. Or a third way would be, to use the design equation. Remember the design equation for CSTR? It was derived for a steady state. So if we use the design equation, we will simply get the value of Ca and Cb and X as well at steady state because the equations were derived with the assumption of steady state operation. Okay, so here we go. We have three different ways to find these values. 4. Determine the system order for both species by examining the obtained differential equations and concentration profile. So you look at the equation and you say, is this a first order system? Is it a second order system? Or you can look at the plot as well. Of course, this question will be more appreciated by the students who already took dynamic course, the simulation and dynamic course, modeling and dynamic, sorry. If you're taking the same this semester, you'll also know what I'm talking about. Okay, otherwise, don't bother, just solve it as simple as it is. So I just solve part 1, 2, and 3 only. Okay, for the first order system, if any, determine the time constant, the steady state gain, and the input or the forcing function. Okay, in order to solve this, make it easy, rewrite the differential mole balance in the standard form of a first order system. Okay, second requirement, the time necessary for the concentration to achieve 99% of its steady state value. So also calculate what's the time required for the concentration to achieve 99% of its steady state value. Compare that time with the time constant. So compare the time required to reach steady state with the time constant of the system, tau p. Is it reasonable for a first order system? Remember we said it should reach steady state 4 to 5 times the time constant. Is it really true in this case for a first order system? Okay, so here's the solution. I'm sharing the solution with you here. CA and CB are plotted. So this is CB, this is CA. You can see that CA reaches steady state way faster than CB. Okay, and if you look at here, CB is kind of an S-shaped, so probably it's a second order system. A is like increasing and then flattening it out, so it's kind of a first order system. Okay, so it's really amazing. See, both A and B are in the same reactor, but they reach steady state at different time. Okay, I'm sharing with you again the solution here. Okay, just a reminder to know how the first order system looks like. Well, it's tau p dy by dt plus y equals kp ft, where tau p is the time constant of the process. Of course, you can either write it this way or you can write it this way, depends which way you are more familiar with. Okay, kp is the steady state gain. Is the steady state. What do you gain when you reach steady state compared to the input, or the static gain, or simply the gain of the process? And zeta is the damping factor or damping coefficient, and ft is the input or the forcing function. Of course, the input in this case would be Ca naught. That would be your input, and you can compare it to the second order system as well. You're familiar with, if you took the course dynamic modeling and dynamics. Okay, that was some insight on that problem. We're gonna also discuss another problem, which is problem 423, production of ethylene glycol again, but this time from ethylene chlorohydrin. Right. The production of ethylene glycol, C, okay, so this is ethylene glycol, given the symbol C, tamam, from ethylene chlorohydrin, this is ethylene chlorohydrin, A, and sodium bicarbonate, B. This is sodium bicarbonate, B. Right, so this reaction occurs the way it's written. As you see, the other products are salt and CO2. So this reaction is carried out in a semi-batch reactor. A 1.5 molar solution of ethylene chlorohydrin. So what is this? 1.5. Obviously, this is the unit of concentration, so it is a concentration. Concentration of what? It's the concentration of ethylene chlorohydrin. So this is Ca naught. So 1.5 molar. Okay, what about it? It's fed at a rate of 30 mole per minute. 30 mole per minute. Again, you look at the unit. Mole per minute. So this must be Fa naught. Exactly. This must be FA naught, FA naught. So it's fed at a rate of 30 mole per minute to 1,500 liters. So this is of blah blah blah. So you're adding A to 1,500 liter of your liquid inside your reactor. So this must be VI, the initial volume. صح? Of course, I'm not going to use V naught because in this setup, naught refers to the input. 1,500 liters of a what? 0.75 molar. Again, this must be concentration. Molar solution of sodium bicarbonate. So this must be concentration. So it is Cb and it is inside the reactor, correct? So I cannot give it the subscript naught, so I give it the subscript I because that's initially, right? That's initially charged to the reactor. Okay. Right. The reaction is elementary and carried out isothermal at 30 degrees C, where the specific reaction rate is 5.1 liter per mole per hour. Make sure, shabab, that you convert the units, time units, so it's either all an hour or a minute. The reactor can hold a maximum of 2,500 liters of liquid. So Vmax is 2,500 liter. Right. Assume that the reaction mixture has a constant density of 1 kg per liter and that CO2 leaves the reaction mixture as fast as it is formed. So CO2 leaves the system, right? Okay, so for CO2, it's a semi-batch system, correct? For A, it's a semi-batch system. For B, it's a batch system. For CO2, it's a semi-batch system as well. So something is leaving the system. Fine. What's required? Perform mole balances on the reactants. Perform mole balance on the reactants. So again, input minus output plus generation equals accumulation. For A, you have input but you don't have output. Tamam. So we have this equation which we kind of developed earlier. Okay, so why it's not going away? Anyway, so let's see. This is for A. So you have input. You have input, correct? You don't have output. You have generation, and you have accumulation. Tamam. And remember, the volume is changing with time. What about B? Well, we don't have input. You don't have output. It's only generation equals accumulation. Tamam. And since it's a semi-batch system, I'm going to work with number of moles. Okay, so I will keep the DNA as is. I'll keep the D and B as is. Okay. So we said V is variable. Remember, Shabab, the logic says after writing the mole balance, if you introduce a variable, you have to provide an equation for. So we have to provide an equation for V. Right. So where you get the equation for V? Yep, absolutely. So we have the mass balance, correct? We have the mass balance from which we can derive an equation for V. Okay, let's look at the mass balance. What does it say? Again, for the mass balance, we can write m dot n minus m dot out equals dm of the system by dt. Okay, so let's look for the mass coming in. The mass coming in. So mass coming in, which could be written as m dot naught, Do we have mass going out? Yes, we do actually. Again, we cannot memorize one equation applied everywhere. Here the mass leaving out is the mass of CO2, correct? And then we have dm by dt. Right, let's look at the mass coming in. How do you write the mass coming in? Well, that's very simple. The mass coming in, it's rho naught times epsilon naught. Oh, that was easy. What about the mass of CO2 leaving the system? Well, let's see what this says. It says, assume blah blah, and assume that CO2 leaves the reaction mixture as fast as it is formed. So the rate at which CO2 is leaving the system equals the rate at which it is formed, correct? Equals the rate at which it is formed. So what is the rate at which CO2 is formed? Well, you know it already, صح? You know it already. So it is the integration of R CO2 dV, correct? For the whole system from 0 to V, where we know that V is variable, correct? But of course here we have to be careful about the units. We have to be careful with the units. So let's see. The unit here, it's mole CO2 per minute, if I'm using minute, correct? Because this is the R of CO2 is mole CO2 per minute per liter, and we have dV is in liters, so you'll get mole CO2 per minute. So that means, however, this guy is kilogram per minute, correct? Kilogram per minute. So what does that mean? This means in order to convert mole CO2 to kilogram, we have to use the molar mass. What's the molar mass of CO2? Well, the molar mass of CO2 is 44 gram per mole, correct? 44 gram per mole. Okay, we have a little bit problem, right? Because if we cancel the mole with the mole, we'll have gram per minute. So that means we need to convert the gram. Okay, so let's convert the gram here. 1000 gram. Let's convert it to kg. So now the gram goes with the gram. We have kg per minute. So that means we have to use the molar mass of CO2. However, we need to divide it by 1000. Okay, so this is, now we have molar mass of CO2 divided by 1000 multiply by RCO2, because RCO2 is not function of volume because the reaction mixtures will mix, so it goes outside, times volume, which is also function of T. Okay, so we have an equation now for m dot CO2. So we have an equation for this guy, we have an equation for this guy, and then we have, let's look at dm by dt, and of course it will be dm by dt. Let me write it down as well. Okay, so dm by dt, of course it will be d rho times volume by dt. Assume the density of the reaction mixture is constant, so rho goes outside, have dv by dt. Then we can assume also that, as I said, rho is constant, so rho equals rho naught. Okay, and then we now have an equation for dm by dt as well. So we can write an equation for dv by dt. Tamam? Okay. So let me see if I have space to write all of this. So this guy basically, yeah, maybe possible. Rho naught dv by dt, and of course you divide by rho naught. Tamam, and then you get an equation for dv by dt. Okay, just to conclude, tamam, just to conclude, let's write the initial conditions. Let's write the initial condition. So what initial conditions do we have? Okay, we have the following initial conditions, right? At t equals to 0, we have Ca equals, what is the concentration of Ca inside the reactor? 0, right? What about Cb? Well, it equals Cbi, correct? Initial, right? Which we have a value for. What about V? V equals also Vi, which we also have a value for. Remember, 1500 liter. I believe this one was 0.75 molar. Okay, so keep this in mind. Okay, what else do you need to think about? What else you need to think about? Okay, I'll have to remove these equations. Tamam. Okay, what do you have to think about here? Like, remember, Shabab? We said the logic is whenever you provide an equation, provide a variable, you need to, whenever you introduce a variable, you need to provide an equation for. So again, we solved the problem with V. Now the rate low, the rate low for RA, and then the stoichiometry. The first thing to do is to relate RB to RA, using stoichiometry. The second thing to do now, okay, let's look at the right hand side of the equation. It's written in terms of number of moles, but the left side of the equation is written in terms of concentration. So that means I need to define the concentration in terms of number of moles, right? So I'll need to write an equation for Cb. What does Cb equal? Well, Cb equals Nb divided by V. What does Ca equals? It equals Na divided by V. Correct? And again, this is V, this is not epsilon, right? Okay, so you have to be careful with this. And of course, you'll need to also relate the rate of formation of CO2 with the rate of consumption of A as well. Right. Okay, what else you need to answer? We'll calculate the time required to achieve 69% conversion of B. Tamam. So that means you have to write an equation for X of B. How do you write the equation for X of B? Well, for B, it's a batch system, صح? So you can write it as NBI minus NB divided by NBI initial. Correct? Okay, and don't forget when you evaluate Shabab, you provide all the parameters as well. Right. Is it possible to achieve the above conversion with the given reactor, and condition Y? If not, then what is the maximum possible conversion? Of course, you have to be aware of the fact that the reactor does not carry more than 2500 liters. Okay, so I think you can do all of this at home, right? And then finally, you're going to plot Ca, Cb, Cc, and Xb versus T, and minus Rb, and V versus T in two separate figures. So I'm going to use two figures only. Okay, this is the solution. And here we're plotting all the concentration, Ca, Cb, Cc, which is my product, and Xb. As you can see, as the reaction progresses, Xb increases, right? Which is good. Tamam. And Cb is decreasing. Why Cb is decreasing? Because Cb you had a charge initially and it's getting consumed. why Ca is increasing? A is also reacting. Why that concentration is increasing? Well, apparently, the rate at which A is added to the reactor is more than the rate at which A is consumed. Correct? That's why it's accumulating within the system. And also the concentration of C is increasing as well. It's a product. Okay. Let's look at the rate and let's look at the volume. The volume is increasing from 1,500 all the way to 2,500. And the rate is increasing at the beginning, reaches the maximum and then decreases. Why is that? Any idea? Any idea why it's increasing and then decreasing? Well, the rate of reaction depends on the concentration of A and B. So you have to look at A and B. Correct? At the beginning, you have high concentration of B, right? And then as you add A, the concentration of A increases from 0 to a certain value. So you have concentration of A is increasing while the concentration of B is decreasing, right? Because B is consumed. So which one wins? Well, the increase in the concentration of A has more effect than the decrease in concentration of B. Therefore, the rate of reaction is increasing and it continues to increase until it reaches a maximum value, after which the rate decreases because now the concentration of B is very low. So any increase in concentration of A will not affect the rate positively because the rate is the concentration of B is very small and it's keep decreasing. So therefore here the concentration of B dominates the rate. So the concentration of B is decreasing. It's small already and it's decreasing further, so it will decrease the rate of reaction. Right. With this, we kind of finish the few of the requirement of this problem. There are other requirements which you can look at in the full slides. Okay, I have one last question related to chapter 4 here, which is test yourself. Okay, let's look at the system here. We have a reaction between A and B, a reaction between A and B to form C and D in this reversible reaction. We have a reversible reaction. Okay, and A is initially charged, B is continuously charged to the system. Okay, let's look at this figure. So we are plotting X and XE versus time. طيب. So as the process, or once the process starts, B is added. So as you keep adding B, more A is converted. So X starts to increase. And since I'm adding more A with time, the equilibrium will be shifted forward. That's why you see XE is increasing with time as well. XE is increasing with time as well because as I add B, the equilibrium shifts forward. We're talking about equilibrium, not the actual situation. Equilibrium conversion increases with time. Hello? Okay, and X increases because we have A is being consumed because of the presence of B. So here it says which figure represents fast reaction and which represents a slow reaction. So what do you think? Why in this figure X superimposes on XE? Why the value of X is equal to XE? What do you think? And why here X is lower than XE? Well, simply because here the kinetic is very slow, right? So you're always below XE except for the end here. Tamam? Well, while this figure represents a fast rate of reaction. It's very fast. The rate of reaction is very fast. It's keep hitting the equilibrium conversion. It's keep reaching the equilibrium conversion. Tamam? So I hope also this adds to you more understanding about equilibrium and equilibrium conversion and the effect of the rate of reaction and its relationship to equilibrium condition. Okay, with this we finish today's lecture, hoping that you found chapter 4 to be interesting. All the best.